Welcome back. We were discussing different types of multiple access. Out of that, we started with the frequency division multiple access FDMA, and we were trying to estimate. First, we tried to understand what is FDMA, very simple way, and then we try to estimate again with lot of assumption and make it very simple. How do we calculate the number of carriers that can be supported by a FDMA technique in a transponder? So, we are going step by step. So, first we have covered in terms of power, when we consider the when we consider total power of the satellite transponder and individual power, the ratio of that, or in dB the difference of that will be in terms of power how many carriers can be supported. Similarly, it can be done in terms of bandwidth. We are discussing that point. So, let us go back to that slide, and this slide, if you recollect, it shows that find the bandwidth available for the all carriers, that is that if it is total transponder, full bandwidth of a transponder. Noise bandwidth of individual carrier. What is noise bandwidth of individual carrier? Depends on modulation, that is the bit rate divided by the spectral efficiency. In case of BPSK, it will be same, QPSK is half, that is divided by 2. So, like that different type of MSK that a number will appear, and then you have once the modulation is done, there is a filter based on the filter roll off factor, the bandwidth will be expanded, and then between the two carriers there are certain guard frequencies given, that guard band factor is taken and the individual carrier bandwidth is taken. So, calculate the number of carrier from the bandwidth requirement. We have BA and BI calculated. It is ratio, or in terms of log you can put it log way also, bandwidth, available bandwidth, noise bandwidth. Once it is in ratio, you can take it in ratio, or if BA and BI are in log term, in dB term, then it will be BA minus BI in log, and the NB also will come in log term, convert back in ratio. So, the numerical value of NB should be rounded to the next lower integer, as I explained last time, that what it will give, this calculation will give is the maximum limit, theoretical limit, that may come out as a fraction of number of transponder, which is not possible. So, the possibility will be lower one, that means you will get some advantage the other way. Now, you have calculated in terms of bandwidth the number of carriers that can be supported. In case of in terms of power, how many can be supported, that is NP and NB. Now, a particular transponder, it gives together the total bandwidth and total power that can be supported. Now, that means whichever number is lower you have to take, the whichever is higher you cannot take, because the satellite cannot, if you do it in terms of bandwidth, it is coming much larger, and you say that is the carriers will support. So, if you put that many carriers in terms of power, you will find it is exceeding EIRP. The other way it is also true. So, therefore, the lower one has to be used, the capacity will be lower of NP and NB, that means both have to be calculated. Now, when it is limited, whichever is lower, if the NP is limited, there is a term, it is called power limited transponder or power limited case. In case of bandwidth is lower, in bandwidth number of carriers that can be supported in terms of bandwidth is lower. So, it is bandwidth limited, whichever is limiting, whichever is lower, it is called that way. So, it is bandwidth limited case or power limited case, you have to take anyway whichever is lower. Some people try to balance it, because the transponders are sold or rented in terms of total power and total bandwidth, how much is taken by the user, both power and bandwidth. So, therefore, people try to balance it, so that maximum advantage can be taken. Best thing is to try a very simple type of calculation, and then we will see what really happens. Some of the calculation. Let us take a quick calculation. Many lot of assumptions are there. It is very simple calculation. Let us say each station is having multiplex 24 terrestrial channel. Forget about terrestrial part. 24 channels are coming, and at each station it is put in TDM, and then it is transmitted as a one carrier, multiple channel, and going as a one carrier, and such many carriers are there. So, it is multiple channel multiple carrier case. So, it transmits as one carrier and the modulation is QPSK modulation. You have to remember the spectral efficiency of QPSK, and the bit rate, multiplexed bit rate is 1.544 megabits per second. Filter roll off factor is 20% of whatever bandwidth you get out of this bit rate and modulation, and then over and above that there is 20% guard band factor. So, how do you calculate? Of course, there are other things given, that is C by N per carrier is 5.5 dB. You see here what is not given is what is the total C by N or C by N naught supported by the transponder. So, it is per carrier given here. Total C by N naught the link can support, now it is given for full transponder is 81 dB hertz. So, for one transponder you try to find out number of FDMA carriers that can be supported by transponder and the number of channels, total channels in the whole network, how many terrestrial channels that can be transmitted. Okay. So, you just remember this, total C by N naught is given, individual C by N naught is not given, we have to work out that. Individual bandwidth is also not given. So, let us see how we proceed. So, individual bandwidth per carrier is in dB form is 10 log of bit rate 1.544 megabit, and because of QPSK it is 1 by 2 multiplied by roll off factor which was 20% of 0.2. So, 1.2, and then whole thing is multiplied by again guard band factor which is 20% 1.2. So, that comes out to be 60.46 dB hertz is bandwidth. So, and it is in dB. So, it is dB hertz. It is just approximated, you can do your calculation, you get a slightly different number depending on your how you do the calculation. So, one thing you try to recollect, that noise power density is noise power divided by the bandwidth. So, N naught is N by B. So, C by N naught is C by N into B, that is N by the denominator N by B, or you can say C by N into B, which is C by N naught is C by N plus P in dB. This is in part of dB, this part is in ratio. So, C by N naught ith carrier, each individual carrier, all carriers are same, each individual carrier is C by N I plus the bandwidth I. Now, C by N I is given, if you remember, C by N was given as 5.5 dB and bandwidth we have calculated. So, C by N naught of individual carrier we have calculated as 65.96 dB hertz. So, therefore, the number of carriers, now we have total C by N naught is specified and individual C by N naught we have got. So, in dB it is subtracted and we get a number like 15.04 dB, which convert into ratio we get it 31.91 carriers, which is maximum that is possible, because it based on total C by N naught that is available. So, 31.91 is the maximum is possible. So, we cannot make it 32 because that will violate that total C by N naught. So, you have to transmit 31 carrier. So, you will have some extra bandwidth is available, that is the advantage. Again, if you do the calculation, your efficiency will be different, and maybe that extra carrier space what you get 0.91 can be distributed in terms of guard band or in terms of slightly loose filters, whichever way. But here is 31 carrier is maximum possible in this particular case. Let us take one more case. Okay, number of channels we forgot one point, that is one more question was there, number of channels in full transponder. So, that is number of TDM channel per carrier multiplied by the total number of carrier. So, that was 24 channel per carrier and 31 carriers. So, in this transponder total 744 channels transmissions are possible. Okay. Now, let us take another problem in terms of EIRP. That last one was on in terms of C by N. So, it is a 36 megahertz transponder that has a maximum EIRP of 50 dBW. Last time it was given C by N naught 81 dB hertz. So, it has multiple carriers, and here other information is given is receive station G by T is minus 10 dB per K. Just don't take this number as it is and don't do the calculation, think a little. G by T is negative, so gain is very low. Gain is very low. Normally these type of negative G by T stations are very small station. Gain is very low. Most probably it is a portable station or satellite phone type of thing. Always look at the number and try to interpret why this number is appearing. Similarly, free space loss is 192 dB, and at 40,000 kilometer, if you do rough back calculation, you will find that this probably it is in lower frequency band, not at Ku band, not at 12 gigahertz. It's much lower. At 12 gigahertz, it comes out to be 205 or 207 dB, depending on range. So this is much lower. This is probably at S band. So try to mentally interpret the number, which may not be useful for this particular problem, but you'll know, you'll enjoy this. Then there is miscellaneous loss 6.6. You can see from the miscellaneous loss larger, so therefore it most probably it is the portable or mobile scenario of the station, because in that case pointing loss and many other losses will come into picture. Miscellaneous loss is larger. Anyway, forget about that. Let's go back to our calculation. That is, each 10 kilohertz carrier needs 45 dB hertz C by N naught. Carrier's bandwidth is very small. Obviously, it's definitely not a video transmission, it's voice or data transmission. Each 10 kilohertz carrier needs 45 dB hertz. So the bandwidth of the carrier is given, and then C by N naught of individual carrier is given. Okay, find the number of carriers that can be supported by the transponder. This is the individual carrier, and the receive side is given fully. So you can find out the transmit EIRP per carrier, and the total ERP is given, and of course bandwidth is also given. This is the noise bandwidth 10 kilohertz, and total bandwidth is given. So you can do it in terms of power and in terms of bandwidth, and then find out whichever is lower. It is that type of problem. Let us look at it. So per carrier ERP is C by N naught minus G by T plus losses plus K. I mean, same transmission equations is written in a different way in terms of EIRP. Per carrier ERP from the satellite, you have to remember. So that is put the numbers from the problem, and you will get 25 dBW. The K value in dB, if you remember, it is minus 228.6. This is all you have to always remember, Boltzmann's constant. Okay, so 25 dBW is per carrier ERP, and total was 50. So NP is available ERP minus per carrier ERP in dB. So it is 50 minus 25 dB. Again you get a fraction 316.22 carriers from the NP, that is from the power point of view. So you take the lower one, otherwise it will violate the available ERP. So you will be working with 316 carriers. Now this is power wise. Let us look at it from bandwidth wise. It is very easy, because individual total bandwidth is already told, 36 megahertz. You can convert into dB hertz, and individual carrier bandwidth is given 10 kilohertz, 40 dB hertz. You can do it in dB hertz and subtract and come back to the number, or you can straightaway divide 36 megahertz by 10 kilohertz, which is available in number. Whichever way is easy for you. So NB is in dB, the available, and here it is done in dB, and we got a number 3600. Obviously 36 megahertz divided by 10 kilohertz is 3600. So NB bandwidth wise, I get there a possibility of put 3600 carriers, whereas power wise it is possible to put only 316 carriers. Somebody can argue, no, I am getting this one is higher, so I should use this. Now just from bandwidth wise it will definitely support, because 10 kilohertz is a bandwidth. But if 3600 carriers are put on the transponder, each carrier is 25 dBW, and convert this 3600 into dB form and add these two, then you will exceed the available ERP 50. So your requirement will be more than 50, which the transponder cannot support. So this example shows that definitely you have to take the lower one, otherwise you are getting into problem. So here out of these two, the lower one is NP 316, So, therefore, it is power limited case. Number of carrier support is 316 and it is based on the power calculation. So, it is a power limited case, this is not a bandwidth limited case, right. So, to improve, you have to improve the individual carrier ERP. That can be improved by various ways, either you select a transponder which has more ERP, or you improve the in terms of losses, or improve in terms of G by T. Losses are a natural thing, so it is better to improve by G by T. Okay, we will see those type of problem of system design later. So, this is one example. Another example, let us take transponder bandwidth ERP is 36 megahertz, it is 50 dBW EIRP, and bandwidth is 36 megahertz. Receive G by T is 30 dB per K. Receive means is a ground station, G by T. Loss is 198.6. Now, you see earlier example it was minus 10 dB per K. Here it is 30 dB per K. So, gain is very large. So, it is a very large station. Obviously, you can have individual ERP much less, but we have increased the bandwidth 1 megahertz instead of 10 kilohertz, and total C by N is 65 dB hertz. No, it is not total, that is individual requirement, because it is 1 megahertz, because C by N, C contains the bit rate. So, 65 dB hertz is the each carrier bandwidth, each carrier C by N not required. So, number of carriers. So, here numbers have changed. So, per carrier EIP is you can put into that transmission equation, you will find it is 5 dBW and total is 50 dBW. So, therefore, 45 dBW dB in terms of number is available, which is a very large number, again fraction, you take the lower integer. So, it is 31,622 carriers. So, since our G by T is higher, your NP has become very good, very large, whereas in terms of bandwidth you have 36 megahertz and 1 megahertz per carrier. So, ratio of that is only 36 carriers. So, here also the other way, that is it is bandwidth limited, because NB is limiting the case. So, it is a bandwidth limited. Transponder can support 36 carriers. So, non-symmetric carriers, individual carrier power can be estimated. This all the basic assumption was all symmetric, but non-symmetric also you have to sum it up by apportioning total power available in terms of occupied bandwidth. You have to sum it up in terms of power and bandwidth. This one small example I will go through quickly. That is, a transponder has 3 carriers in FDMA, has 40 watts saturated output power with output backoff of 3 dB. You can see, so your actual available power is 40 minus 3. Now, bandwidth required by each stations are 15 megahertz, now different bandwidth, 10 megahertz, 5 megahertz, A, B, C. Find the power level for each carrier at the transponder output. So, EIRP per carrier, each carrier will be different because the sizings are different. So, how do you do? Transponder total available power with 3 dB backoff is 3 dB is half power. So, 40 watt divided by 2 is 20 watt, in terms of dBW is 13 dBW. Total bandwidth that is required, each individual station needs different bandwidth. So, total bandwidth required is 30 megahertz. Transponder output power, so you can apportion in terms of bandwidth is 15, this is station A, 15 megahertz required out of 30 megahertz, and total 20 watt is power is available. So, the power should be allotted 15 by 30 is half. So, power should be allotted only 10 watt, which is 10 dBW. And in terms of dB, you can get 13 minus 10 is minus 3 dB is taken by the station A at the transponder. Similarly, for station B, the again bandwidth ratio is 10 by 30, 1/3 of 20 watt. So, 6.6 watt and 8.2 dBW is required, and this is the apportionment in terms of dB. And station C takes 5 by 30 because this is a 5 megahertz bandwidth. So, it takes less power, 3.33 watt, which is in terms of dBW 5.2 dBW, and this is the apportionment. Now, if the satellite gain is 105 dB, then input power to the satellite based on those apportionment, how much power it is transmitted out per carrier from station A, and the gain you subtract. So, input to the satellite from station A is minus 95 dBW. You simply subtract the gain of the satellite. So, each carrier, now what is the input to the satellite coming from that particular station, that is listed here. And then if the 20 watt transponder output can be achieved by transmitting a 250 watt from a station, another way, without knowing the loss, if you can know that how do I saturate the transponder, here it is not saturating with backoff. So, if a 250 watt transmission can generate 20 watt output, find the ERP. So, again the apportionment of that 250 watt is 24 dBW. So, 24 dBW minus 3, that is 21 dBW, this is 125 watt from station A, 83 watt, 0.3 watt is station B, station C 41.6 watt. And these are another way of calculation, which is simply by apportionment of power and bandwidth. Okay, now let us get into some more issues on FDMA. People try to take advantage of that when we talk about voice, it is not continuous. So, that non-continuity, use of the channel by voice, that can be utilized. We have seen that FDMA is most efficient when continuous traffic is there. So, there is non-continuous traffic that you can know. I hope you are aware of this, that voice is inactive many times. When I am speaking to you, between sentences I put a pause, between two words I put pause. So, there are a lot of inactivity. So, a complete channel given to me for this transmission, there are a lot of time I am not using. For a long time, if it is observed, people have seen that it is 40% time it is not used. So, voice activity is 40%, 60% time is not used. Okay. That is that is a statistical estimate people have done by research. So, if there are multiple voice carriers and each has 45 kilohertz bandwidth in 36 megahertz. So, just ratio of these two, that many voice carriers can be supported, which is nothing but 800, 36 megahertz by 45 kilohertz is 800 voice channel can be supported. But always these 800 voice channel are not busy, only 40% of that is busy. So, therefore, actually at a time, at any instant snapshot if you take, at the transponder only 320 carriers are present, but satellite is giving that much bandwidth and that much power. So, bandwidth wise and power wise 60% of that is not used at any time. So, how we can use? Each carrier needs some bandwidth and power from the transponder. So, this reduction of this carrier in number of carriers, you get an advantage of power and bandwidth. Let us look at the power. It can be utilized in a network by increasing the forward channel power at the transponder, reducing the G by T of the user terminal, or increasing the coverage contour. Various ways it can be interpreted, or allotting more voice channel. Okay, ideally it is true, but many people do it in lower delay network, but in case of satellite it is very difficult. By the time you detect a voice activity and do a allotment, and the receiver has to know that which particular frequency is allotted to him. So, this allotment procedure takes each is one hop. So, allotment procedure will take some time, and you have to hold the voice for that. So, it is not suitable for with a large propagation delay network, but for a small propagation delay network it is theoretically possible. It can allot more voice channel. In this satellite case it is not always used, but you can do the other things in terms of power. Now, that very in short we have covered the interesting some aspects of FDMA and how the capacity of the FDMA can be achieved and really calculated in terms of power and bandwidth, and we have given certain examples, quick examples of the full transponder mode, that is over 36 megahertz, how it can be used. And then the same thing is true for a smaller bandwidth allotment of the transponder in terms of power and bandwidth. Now, let us go into the another multiple access technique which is quite popular, which is called TDMA, that is time division multiple access. Let us see on that. So, time division multiple access, here the resource, that is the bandwidth and power available from the satellite, is shared by one terminal at a time. That is, one terminal is given the full bandwidth and full power available at the satellite. But then to do that, say let us say voice is going and you have some 12 stations. So, other 11 stations have to hold the voice, and then whenever their term comes they have to transmit. So, this can be done by compressing the continuous input into a high bit rate burst. If there is continuous inputs are coming, you can compress it into high bit rate, and in 1 bit period you can allot to each of them. So, then one big advantage is that you have got full bandwidth and full EIRP, and there is no multiple carriers. So, TWTA can be operated at the near saturation, that means maximum power you are extracting. You are not coming down to linear region by putting some back off. Biggest advantage. Disadvantage is you increase the bit rate, and operating TWTA at near saturation means you can increase the coverage contour, or the G by T of the stations, receive stations can be reduced. So, no intermodulation, there is only one carrier present at a time, and you are not operating in the back off, that is, this is the nonlinear, you are operating at this saturation point, single carrier saturation power. Since the time is complete for this period, we will continue the discussion in the next period. For the time being, thank you very much.